Hi everyone, welcome to lesson 11 of the Advanced Higher Stats course. In this lesson, we're looking at normal approximations. Find the skill on page 22 and 23 on the Advanced Higher course spec. By the end of this lesson, you should understand the conditions which allow normal approximations to take place regarding binomial and Poisson distributions. You should know how to calculate the parameters of an approximated normal distribution. You should be able to answer questions which require normal approximations, and you should be successful in using continuity corrections. Are some general conditions for a normal approximation. One is independent observations. This means that one point should not affect another point. So what that means is, let's say the average number of people in a plane is 100. We assume that those people are not related. So there's no family of four where either those four would appear on the plane or those four would not appear on the plane. The next is a large sample size. This varies depending on if it's a binomial or a Poisson, and the shape of the population is approximately normally distributed. So what that means, it follows roughly a shape like this. Now, more specifically, the conditions for a binomial would be NP is greater than or equal to 5. So N is the sample size and P is the probability of success. Where, let's say, in a coin toss, it would be 0.5 if you count heads as a success. And Q should be greater than and or equal to 5. Q is the probability of failure. So if you wanted heads in a coin flip and you got a tail, that would also be 0.5. And then sample size is greater than 20. Shape of distribution should not be too skewed, so it should follow a normal distribution. And you also have to implement a continuity correction for the binomial. For Poisson, lambda should be greater than or equal to 10. And how I remember this is by, on our tables for the Poisson table in our data booklet, the table we're given goes up to 10. So if we can't use the table for a Poisson question, most likely we have to do a normal approximation. And again, the shape of the Poisson distribution should not be too skewed. It should be close to the normal distribution. And you should also implement a continuity correction. Now let's move on to finding the parameters of approximated normal distributions. So for a normal distribution, our parameters are mu and sigma squared. And when we are given a binomial distribution, we can check the table here, binomial parameters, sorry, and we are given the sample size, which is 13, and the probability of success, which is 0.3. So how do we get the mean? This is very simple. We just look in the table. We can see here that for the binomial distribution, the mean is NP. So if we want that for an approximated normal parameters, it's 30 times 0.3, which is 9. Now we also want sigma squared, which is variance. And that gives us this. 1 minus p is q. So for variance, we do times n times p times q. And that should give us 6.3. Okay, next on to Poisson. So what does Poisson give us? It gives us lambda. So we know 13 is lambda, but how does that help with means and variances? Well, it's very simple. To find the mean in a Poisson distribution, the mean is lambda. So n is equal to lambda, which is 13. And that's the same for variance. So our normal distribution is 13, 13. And that's very simple, easy. Moving on, back to binomial. We have n, which is 24, and we have p, which is 0.5. So 24 times 0.5 gives us 10.8, which is the mean. So we've done 24 times 0.45. Now we need to find the variance, which is NPQ. So 24 times 0.45 times 0.55, and that gives us 5.94. Now the final one, Poisson again, the lambda is 24, so it's just N24, 24. Now let's figure out if we can normally approximate the following distribution. We have binomial 30 and 0.2. We have three criteria this distribution has to meet. N is greater than 20, which it is, and P is greater than 5 or equal to 5. So 30 times 0.2 is 6, which is equal to or greater than 5, so that's good. And NQ is 24, which is also greater than or equal to 5, so it can be normally approximated. We'll put a tick there. Next is 15 and 0.1. N is not greater than 20. We can't normally approximate this. And same with here as well. We can't normally approximate this. Next up, we have Poisson distributions. So for the Poisson distribution, lambda has to be greater than or equal to 10. And it's not here. So we can't normally approximate this. We can normally approximate this because it's greater than 10, and the same for this one. When normally approximating a discrete distribution like binomial or Poisson distributions, we have to do something called a continuity correction. This is because we're going from a discrete variable to a continuous variable. And I will have a video linked in the description which looks at this in more detail, and that might help you if you aren't able to understand from my explanation. So let's say you have the following data about the number of redrafts done of a personal statement throughout the whole year. The most common being 3, and then you have 4, 5, 6, 2, 1, 0, and this roughly makes a normal distribution. These are discrete variables. So when you do make a normal distribution, it goes from a discrete variable to a continuous one like this. Now, one thing I want you to realize is that in this discrete variable, there's no 3.5. There's nothing like that. You can't have 3.5 redrafts, or you can't have the probability of there being 3.5 redrafts or less, anything like that. But in this normal distribution, you can, because it's continuous. So how does that work? So that means that in this discrete distribution, if I ask you the probability of x being 4, in this continuity corrected one, I would be asking you for probability of 3.5, well, of x being between 3.5 and 4.5. Because these discrete numbers kind of, they become a range. So 3 would become 3.5 to 2.5. 2 would become 2.5 to 1.5. 1 would become 1.5 to 0.5. 4 to 3, 4 becomes 3.5 to 4.5. 5 becomes 4.5 to 5.5. You get the deal. And this is something we have to be considerate of. And I think that we look at that in the next slides. Let's test our continuity correction with this question. Normally approximate binomial 30 for n 0.6, hence find the probability of x being smaller than 17. The first thing we do is we write the parameters, which is 18 and 7.2. Next, how I like to think about this question is if I was asked to find the probability of x being 17, I find the probability in this approximated distribution, I find a probability of 16.5 being smaller than or equal to x, which is smaller than or equal to 17.5. So what that means is if I want the probability of x to be less than 17, I want the probability of x to be less than 16.5, if that makes sense. So what I would do here is I find a z value, 16.5 minus 18 over root 7.2, because it's divided by sigma, and that gives us a negative 0.56. This is a negative number, so I want to be a bit careful. What I would do here is I would draw the normal distribution and just kind of visualize everything. The mean will be roughly here, 16.5 will be roughly here, and I want to find this area here. So how I can do that is I can find the opposite area and do 1 minus, and that's what I'll do because it's a negative number. The table is only for positive numbers. So the probability of z being less than or equal to negative 0.56 is equal to 1 minus the probability of z being less than or equal to 0.56 which gives me 1 minus, and then we look at the table, 0.56. So that will give us 0.7123, which right here, 0.7123, and that gives us 0.2877. Next question is find the probability of x being greater than 21. Again, if I was asked to find the probability of x being 21, I look at a range from 20.5 to 21.5. That means I need to find the probability of x being greater than 21.5. So I find the z value first, 21.5 over 18, minus 18 over root 7.2. And that gives me 1.3. And here I would draw the table as well, not the distribution. This is the mean. This is roughly 21. I want to find this area. So what I can do is I can find the opposite area and do 1 minus, which is exactly what I'm going to do. The probability of z being greater than 1.3 is equal to 1 minus the probability of z being less than or equal to 1.3, which is 1 minus, and then we look at the table, 1.3 exactly, so that's 0.9032. 0.9032, and that gives us 0.0968. Try the same thing, but for Poisson distributions. Normally approximate Poisson 45, and hence find probability of x being smaller than 47. Now, we need lambda to get the normal parameters here, and lambda is 45. So our normal distribution is 45, 45, very simple. Find the probability of x being less than 47. So if I was asked to find a probability of x being 47, it would be between 46.5 and 47.5. So that means if I want it to be less than, it would be 46.5 minus 45 over root 45. And that gives me 0.22. Now, if I want the probability of z being less than or equal to 0.22, that would give me, and I look in the table here, 0.22. So 0.5871 is the answer there. 0.5871. The end of this lesson. I will have linked the video, so make sure to check it out for a better understanding of the continuity correction. And by now you should understand the conditions which allow a normal approximation to a binomial and Poisson distribution. You should know how to calculate the parameters of an approximated normal distribution. You should understand how to answer the questions which require normal approximations, and you should be successful in using the continuity correction.